Alright, ladies and gentlemen, this problem here is very exciting. So if you have a moment, run over there to the cabinet, grab yourself a bag of popcorn, throw it in the microwave, and grab a soda, because this is going to be good. First, to find the value of x in this equation. Notice the right side's equal to 0. If we were to add 5 times x to the log of 5 to both sides, we would be given this. If we were then to apply log to both sides of the equation, that's fine if you do it to one side as long as you do it to the other. Then using the power property, the exponents for arguments can be moved as coefficients. So oddly enough, our coefficients are logarithms. The log of 3 that was an exponent is now a coefficient. The log of 5 that was an exponent is now a coefficient. If you then rewrite the log of 3x using the quotient property that says if you are multiplying your arguments, you can write that as adding separate logarithms with the same base. Do the same thing with log of 5x, you get log of 5 plus log of x. Notice the yellow changed to the yellow, the green changed to the green. If you then use the distributive property, multiply log of 3 times log of 3 and times log of x. Multiply log of 5 times log of 5 and log of x. When you multiply something by itself, it becomes squared. That's why it's log of 3 squared. And that's why it's log of 5 squared. Notice that log of 3 quantity squared is the same thing as saying log squared of 3. It's the same meaning, you just write it a little bit different. So I'm going to write it without the parentheses because it looks nicer without the parentheses. As we continue, this is the same thing was on the other page. My goal now is to get all the terms with x's in them on the same side of the equation. Terms without x's on the other side. There are currently 4 terms. 1, 2, 3, 4. So if I want my terms without x's on the right, I want to subtract log squared of 3 from both sides. Which I wouldn't show this work if I were you. I just want to make sure that you follow. That's why I'm writing it down here in a light color. Also, if I want log of 5 times log of x on the left, I got to subtract that from both sides. Notice that even though we have 4 terms, none of them are like terms. So on the left, I have log of 3 times log of x minus log of 5 log of x. On the right, I have log squared of 5 minus log squared of 3. On the left then, ultimately I'm trying to get x by itself. There's 2 x's in this problem. Since each x is being multiplied as part of a multiplication of 2 different terms, I want to factor out that log of x, which is what just happened. Each of these terms had a log of x. I factor them out to the beginning, giving me this. Right side's going to stay the same. I'm trying to get x by itself, so I'm going to divide both sides by log of 3 minus log of 5. I notice that my numerator can be factored. Log squared of 5 minus log squared of 3 factors into log of 5 minus log of 3 times log of 5 plus log of 3. That's called the difference of 2 squares. In comparing what I have here in my numerator and my previous denominator, I'd like to cross things off, see if they cancel. This one over here is close, log of 5 minus log of 3, but the signs are wrong. What I can do to fix that is take my denominator and factor out a -1. By factoring out a -1, it changes the signs, but it doesn't change the value because there's still a -1 out front. Once again, I factored out a -1. Then I can cancel those common factors, which leaves me with log of x equals log of 5 plus log of 3 all divided by -1, which of course, if you take the negative to the top, each term gets a negative, like so. Almost finished. Using the power property, I can take the coefficient of -1 and write it as an exponent for each of my arguments. 5 to the negative 1 means 1/5. 3 to the negative 1 means 1/3. Then using the product property, multiply my arguments, a fifth times a third, and I get 1/15. Now using the property of equality, we get x equals 1/15. Tell me that wasn't fun. 14. The intensity of an earthquake is described by a number on the Richter scale. The Richter scale number R of an earthquake is given by the formula R equals log of A divided by T plus B, where A is the amplitude of the vertical ground motion in microns, T is the period of the seismic wave in seconds, and B is a factor that accounts for the awakening of the seismic waves. Find the intensity of an earthquake to the nearest tenth, that's 1 decimal place, if a recording station measured the magnitude of 200 microns in a period of 1.6 seconds and B equals 4.2. I'd first write down the formula without the letters. Quick and easy, it says that B is 4.2. I replace B with 4.2. T is the period. It says that it's 1.6 seconds. A is the amplitude in microns. We have our microns as 200. So we fill those numbers in appropriately. 200 divided by 1.6 is 125. This is the best we can do without rounding, so you don't put this in your calculator. When you put it in your calculator, it's going to automatically start a parentheses around 125. You have to finish it. Put that in your calculator and you get about 6.3. Part B, how much more intense is an earthquake at magnitude 5 on a Richter scale than an earthquake that measures 4 on the Richter scale? If you break this down to its basic parts, if the Richter scale measured 5, notice there's no base for a logarithm. That means it's a base of 10. So 5 equals log base 10 of some number. We don't care what this number is. Comparing that to 4 equals log base 10 of some number. If you take those logarithmic functions and write them in exponential form, here's what you'll notice. You get 10 to the 5th, you get 10 to the 4th. What this question is really asking you is, how much bigger is 10 to the 5th than 10 to the 4th? Well, of course it's 10 times bigger. That's what it means to be an exponent. It means how many times you're multiplying it by itself. 10 to the 5th, you're multiplying it 5 times. 10 to the 4th, you're multiplying it 4 times. So it's 10 times bigger. 15. The parallax of a star is the difference in direction of the star as seen from two widely separated points. Astronomers use the parallax of a star to determine its distance from Earth. The apparent magnitude of a star is its brightness as observed from Earth. The apparent magnitude of a star is its brightness as observed from Earth. Astronomers use parsecs to measure interstellar space. 1 parsec is about 3.26 light years, or 19.2 trillion miles. So far, everything that we've read, pretty sure is pointless as far as figuring out this problem. The absolute magnitude is the magnitude of a star that... The absolute magnitude is the magnitude a star would have if it were 10 parsecs from Earth. I think that's also worthless. The greater magnitude of a star, the fainter the star appears. I think it's also worthless. For stars, for stars, more than 30 parsecs, or 7.576 trillion miles from Earth, the formula relating the parallax P and the absolute magnitude M and the apparent magnitude is this formula. I'm going to write down this formula in color code for your viewing pleasure. As we go to our first question, this problem tells us, hey, the apparent magnitude is 5.3, put in for little m. It says the parallax is 0.018, put it in for p. That's all you have to do. 5.3 and 5 is 10.3. That's the best you can do without a calculator. Put it in, you get 1.58. A lot of words. Break it down to just the parts that you need, and it's pretty simple. Part B, stars with apparent magnitudes greater than 5 can be seen only with a telescope. If a star has an absolute magnitude of 8.6, that's capital M. Has an apparent magnitude, that's lowercase m. An absolute magnitude of 5.3, that's capital M. Find its parallax. You put the numbers in, you're trying to get P by itself. If you were to subtract 5 from both sides, you get 0.3 equals 8.6 plus 5 log of 3, or log of P. If you subtract 8.6 from both sides, divide both sides by 5. anti-log both sides, which means 10 to the exponent. Put that in your calculator, you get 0.0219.